Hello, students. Welcome to Global Climate Change. This is lecture 9. We basically will be talking today about climate models, scenarios, and what the future basically, what the models are showing the future are going to look like, and some possible scenarios that the future might look like. So this week, your reading will be, as it says down here, chapter 4, pages 1 through 44. So please read that. That should prepare you. So let's get started. All right, so what is a climate model? A climate model is a mathematical representation of the physical processes that control the climate. So that's basically everything that affects the climate. And remember, when we're talking about everything that affects the climate, we're talking about all the spheres. So that would be the sun, the atmosphere, the hydrosphere, the cryosphere, the biosphere, solid earth. There's many different things that interact together as we've went over before, and that can actually influence our climate. Now, it's important to remember that within these models are equations, and that's how it determines what, the output's going to be. And so the equations are very complex that are inside of these models. It's not simple math by any means, and it's many different equations being solved simultaneously at the same time because it's got to take into account all the spheres and all the interactions. So some of the world's largest supercomputers are running climate models. Over at NASA, at Ames, here in Mountain View, we have the 12th largest computer on the planet. And I know from when I was there that some of the simulations and models actually are running on that computer. So pretty cool stuff here going on in the Bay, even just with NASA. So there is a need for climate models. Why do we need them? Because we're already seeing effects of global warming. So 9 of the 10 warmest years during the instrumental record have occurred in the past 15 years. That's kind of insane if you really think about when did instrumental records begin? It was in the early 1900s. So we're talking about over 100 years worth of data. 9 of the 10 warmest years have occurred in the past 15. So they've all been in recent times. The September Arctic sea ice extent was 50% lower in 2012 than in 1979. The global average sea level rose by 20 centimeters, around 8 inches, from 1900 to 2000. It might not sound a lot, but think about Florida. How far above sea level is Florida sitting? Not very much. I think it's a foot. So, 8 inches actually matters when we're talking about areas of the country or even the world that are extremely close to sea level. Climate models allow one to not only verify the causes of global warming, but also examine how the climate will change in the coming decades. So they actually serve two purposes for us. First, what's going to happen in the future, but also for us to understand and verify what we think the causes actually are. Because, if we feed it certain things like, say, less CO2 and start running it in 1900 and see what it thinks it's going to be like today, and it doesn't match today, then that will tell us something. We'll get into that a little bit later on here in the lecture. Okay, so the core concepts of these models, global climate models or GCMs, are to separate Earth into at least two sections, okay? At least. So there can be many more sections, but at least it'll separate it into the atmosphere and the ocean. Each section is then further broken up into submodels, and the GCMs break up Earth into grid boxes, each of which obey the laws of physics. So it actually has these grid boxes, and it puts these all over the planet. And then there's equations that it will solve inside each grid box, and then kind of go throughout, keep moving from grid to grid. So this is kind of an example of what one of the supercomputers here looks like. The model accuracy improves as grid boxes become smaller, so when the resolution actually becomes finer, and time step decreases. So as we look in finer time detail as well. However, this increases the running time because it has to do more equations, exponentially, because it's talking about many, many, many different grids. And over time, the model resolution has increased. So, we keep being able to make these grids smaller and smaller, and the time increments smaller and smaller as well. Okay, so here's some elements of the global climate model. Separate models characterize processes in the atmosphere, oceans, land, sea, and sea ice. I'm sorry. So, I said that it's going to separate them into at least two different areas. And I said, it can definitely do it into many more. So these are examples of the different areas that I actually do separate models for. I might do one for just incoming solar energy and another one with snow cover, and then look at how those two, combine. It might do many different things with all these different processes that the Earth has going on. So here's kind of a genealogy of global climate models. Now, the black arrows are going to be direct lines of development, so it's going to go from like here to here and then, to now, because this is the timeline here on the bottom. Okay. The white arrows are going to be major influences. So, this GFDL model is going to influence the ANMRC model, but then that output's actually going to go back and influence the GFDL model again. And then a bar like right here or right here is going to be basically when it stopped development. Okay, so you can see how this UCLA actually influenced NASA's model, also the Navy models, some other things here, the RAND model, and then that influenced or led into the OSU model. So all these models are kind of like influencing each other and kind of helping each other out. So here's kind of an example of what those grid boxes might look like. Oops, sorry. Maybe I should have made this slide a little bit bigger. Hopefully you guys can see the fact that these kind of look like little honeycombs. Where's my cursor? Here we go. Little honeycombs here all over the Earth, and that would symbolize all these different grid boxes that it would have. And these global climate models characterize fluxes into and out of a grid box during a time step. So, it's going to look at the flux like both out of it and into it, up, in all different directions, north, south, east, west, and also up into the atmosphere. So this is why, they're running so many different equations at the same time because, it's definitely going to be looking at all these simultaneously. This is almost impossible for human beings to do. So computers have really helped us with this. So, every model, if any of you guys are comp sci majors or, like myself who do, neural networking models, things like that, we know that there's input and then there's output to these things, right? So, the input is going to be the changes in atmospheric greenhouse gas concentrations, changes in albedo due to aerosols. These are going to be like kind of examples of what we might use as input, and then we're going to send it to the model. It's going to do all these, these grids, and it's going to do these equations, and then it'll output what the future, how temperature, precipitation, or sea level might change. So it's going to give us like kind of different numbers on different things and tell us how the changes will happen or might happen. And the reason why I say might happen is because we use scenarios to figure out the range of possibilities. So because it's unknown exactly how emissions will change in the future, scenarios have been developed, okay? Scenarios, if I can't say this correctly. What factors can affect greenhouse gas emissions? So basically we're saying here that what factors can affect the greenhouse gas emissions and how much of it's going to go, like if it's going to go up, if it's going to go down, if aerosols are going to go up or go down. But there's factors that actually influence how much we're actually emitting. So then if we look at different scenarios and figure that out, then we can actually figure out this range of possibilities. Like how much can we cut greenhouse gases? How much is feasible? And in what period of time can it even happen in? It's impossible for us to just tomorrow, say we're going to be done with greenhouse gases and we're just going to stop emitting them tomorrow. Like there's no way we could do that because what's going to actually like power us and what's going to like replace all this energy and everything else, obviously it's going to take some time to flip over. So it kind of looks at like what we can do, like what's going to change and how different economies might change and things like that. So here's these factors, like I was kind of saying here, is a global population. So like how many people will there be? Because obviously we need more energy, we need more food, different things like that, to feed, a higher population. Currently at 7+ billion projected to increase. So we're looking to probably have to feed and power more people in the future. Energy generation. So are we going to continue using fossil fuels? Or are we going to use, renewable energies like wind, solar, things like that? Or are we going to find something else? economic growth. So different countries might be in the middle of, doing their, growing economically themselves. And so it depends on like how they grow and how they choose to use energy, things like that. Also the type of economy. So are they a material based or a science and technology based economy? And also, are they open to cooperation among countries? Everyone's culture is going to be different. And so, are they going to accept help or are they going to give help when it comes to cooperation? If they're going to be more homogeneous and share technologies or more isolated, and then, or in also have a greater separation between the rich and the poor. Why is this not advancing? Okay, so these scenarios are going to be kind of like storylines. So, a high emission scenario is going to be a world of rapid economic growth and rapid introduction of new and more efficient technologies. So like that story is going to look a lot different than, low emission scenario where we have a world of dematerialization and an introduction of clean technologies. So it kind of depends like how our world evolves through time and what the story of our planet actually looks like between now and like 2050. So there's four main storyline scenarios. We have A1, A2, B1, and B2. And if you see, we kind of have it set up on a quadrant type of table here. Okay, so up here is going to be more economic, down here be more environmental, to the right will be more regional, and to the left will be more global. So A1 is going to be more economic and global, where B2 would be regional and environmental. Okay, so you can kind of have an idea as to like what or we're trying to have an idea at least as to like the different possibilities that our globe might look like in the future. Okay, so here's what, so if we can remember that A1, A2, B1, B2, here's the different quadrants here, A1, A2, B1, B2, and from here and here is going to be the range of possibilities of what might happen. And the most likely scenario here is going to be in red. And there's going to be a couple like sub scenarios as well, like this A1F1 and A1B. It's going to look like these two lines are going to be, close together here because we already basically know there is no real question as to what the range of possibilities could have been in the year 2000 because it's already passed. So, and then as it gets, you can see here, like for instance, this one is less unsure the further out it goes. This one, most unsure, looks like right around the 2050 timeline. So you can kind of see how, this A2 possibility is about maybe the A1 is probably, let's go back here, which could be where people are more economic and then more regional. So they're going to be thinking about themselves more, and they're going to be thinking about money more, and put those in the most high importancy. That's probably our worst case scenario at this specific point. And remember, this is globally. This is not just the United States. This is everyone on the globe and all the different countries. Okay, so the A1 storyline, just to kind of go into these storylines a little bit more. It's going to be a world of rapid economic growth. The population will peak in the year 2050. And then remember I said there's like a couple different subcategories here. So A1F1 is going to be where, fossil fuel intensive. So, when the globe uses more fossil fuels. A1T is going to be non-fossil intensive energy use, where it's going to be more technology. A1B is going to be like a balance between fossil and non-fossil. Non-fossil being like, wind turbine, solar, things like that. The A2 storyline is going to be a heterogeneous world. Technologies are not shared across borders, and the population just continues to rise. So it just continues to be more and more people to feed, and there'll be continued to be more and more people to, give power to, and, vehicles, more cars driving around, transportation, things like that. So the B1 storyline will be similar to the population as A1, which would peak in 2050. And the global exchange cooperation between countries. So there will be cooperation between countries in this scenario, though, and they'll be focused on social and economic sustainability. Where the B2 storyline is going to be the population is more like A2. Whoops, and remember, A2 is going to be where the population continues to increase, and the similar environmental social focus like B1. Okay, so we'll go back over, and environmental focus is going to be where technologies are not shared across the borders. I'm sorry, similar environmental social focus like B1. So it's going to be a global exchange of cooperation between countries. So, and also a more heterogeneous world where people are more, talking to each other and more, likely to share their ideas between each other. And then they're thinking more globally and not just about their country alone. Okay, and the past and predicted changes in global average atmospheric CO2 concentrations. So this is going to be kind of like, this is going to be the past, like what's happened, okay? And then right around here is when the model would have began, okay? Because these are the observations, right, in the black line. So this would be where the model began, and then it's going to say, what are the projected, what do these different scenarios say about what the global average CO2, would look like? So the A1F1, is obviously going to be the worst case scenario where we go over, 1,000 parts per million. Okay. And the best case scenario is going to be the B1 where we peak, it looks like, because it looks like it's starting to go down here, right around at 550 parts per million. The A1T, it looks like it's peaked as well, close to 600. But, like this one seems like it's going to keep going. This one as well. So, and it doesn't have in this graph at least, past that. So how do we know, right? Like, how do we know if this can be, or if this is true and how true it might actually be? We know this by verifying the models. And yes, verifying them can be done. Okay, because if you look, and if you caught when I said back, I think it was back here, like why would we start the model here, right? When these are the observations. These are going to be the observations, but we started it kind of like in here-ish, right? That why would we do that? It's because, a lot of the times to verify the model, they'll start it here and then see where does it look like here? And then what do the observations look like here? So if the model is handling like right now correctly, if we started it, in the late 1800s, then we can know, with more confidence or very good confidence, that this model is actually running correctly because it was able to predict what's happening right now accurately. Okay, so another way of saying it is if a climate model can simulate the past climate, then there is a reasonable chance that the model can accurately predict the future climate. Okay, and here's like, can we predict changes in past climates? Yes, we can. Okay, so here's our temperature anomaly in the global land ocean temperature index. Here's our annual mean with the 5-year running mean. And it does pretty good here. Same thing with the natural, anthropogenic, and observed. This natural and anthropogenic is pretty spot on, and so is anthropogenic. I mean, if you look, the red line kind of like pretty well follows, where some of these other ones kind of like diverge. It's because, if we take the natural alone, remember I said the input's going to be the greenhouse gases. So if we just take like natural forcing alone, it doesn't even look the same, right? It ends up right here. If we look at anthropogenic alone, okay, it's going to end up the same. It looks like it has a little bit of divergence here from the observed, in the meantime, but it pretty well goes in line, once it hits the year, was this 1980 or so. And the natural and anthropogenic is actually this red line, and that's the one I think is closest actually, like consistently along with what's going on. And this one is pretty well in line as of 1970. So this is kind of like how we know, okay, it's not just natural forcing that's causing us to warm. We are looking at these models and we're saying, wow, it handled it correctly between 1870 and now it's pretty spot on, and so we can verify it, and we can also know that it has got to be a mixture of natural and anthropogenic causes that's making us warm. The conclusions here would be the models can reasonably predict the temperature variations over the last 150 years, and that most of the observed warming in the past 50 years is attributable to human activities. Some words I just can't say. All right, so here's going to be another graph basically of these scenarios, the year 2000, these being, the observed again, and it's basically going to give us, what the global surface warming, the range that the model is basically saying, like, from this range to this range is possible, with this one being the most likely thing, by different scenario here. In 2000 to 2100 global warming based on 6 emission scenarios. Best estimates are going to be 3.2 to 7.2 degrees Fahrenheit, with the likely range being 1.8 to 11.8. Now remember, we saw a 2.39 degree Fahrenheit rise from 1960 to 2016. So in 100 years, we saw 2 degrees, 2.3 degrees, or 2.4. But our best estimates are saying that they're going to at least be 3.2, likely be between 1.8 and 11.8. So, if we don't change things, it's kind of looking like we're going to get a lot warmer. The changes in temperature, future changes in surface temperature are not going to uniformly be distributed around the globe. So, the poles are actually going to get warmer. Their change in temperature is actually going to be greater than, here in the mid-latitudes or, down at the equator. The land surface temperatures are expected to increase more than sea surface temperatures, which makes sense because, oceans takes a lot longer to heat and cool than land does. And Arctic regions are likely to warm more than any other latitude. I just said that. The reason why is albedo will be changing. Okay, so polar and equatorial regions are likely to become wetter. Mid-latitude regions will become drier. And then overall precipitation should increase. Warmer air can hold more water vapor. That's the reason why. Those molecules in warmer air are moving around a lot faster, and it gives the water vapor molecules more room in between. So that's the reason why it can actually hold more, which would also lead to more clouds and precipitation. And I think I've already showed you guys a similar graph to this when we were talking about sea ice and sea level. The sea ice has been steadily declining, and the level of the sea level has been steadily rising. This is a little bit different though, because it actually shows you how the different scenarios actually would affect the sea level rise. Best case scenario is going to be that, let's see, 0.8 meter. This is in meters. Where right here, that A1F1 is going to be closer to, about 1 meter. Okay, so the sea level will increase. Why? Because of thermal expansion and also because of melting of continental ice and snow. So, I'm from Nebraska, so I've seen a lot of people talk about, if you put ice inside of a glass of water and you melt it, the level of the water doesn't change, so why are we saying that the sea level would rise? But I think that they're not thinking about the amount of ice and snow that we actually have is on land, that once that melts, then that would be introduced into the oceans, and that is going to increase the sea level. So if it gets warmer, expand. So sea ice area decline, warmer temperatures lead to sea ice melt, and the process will be accelerated by ice albedo feedback. Remember, less ice, right, means that more absorption and less reflection. So it actually, because of feedback, it's a positive feedback, it'll actually cause it to get warmer. 2 climate models projected from around 2007 show ice-free Arctic summers by 2050 or 2070. That's only 30 years away. So, if you're sitting there right now and you're like 20 years old and you're 2050, you'll be, well, 50. That's funny. I guess, been born in the year 2000. I don't even think about that. I guess I'm old. But yeah, so, um, yeah, so by the time you're 50, if you're sitting here right now listening to this and you're 20, then, you could see ice-free Arctic summers. Let's hope not. And recent trends show that it could be sooner. All right, now hurricane intensity. As ocean temperatures increase, there'll be more energy for hurricanes. One of the ingredients actually for a hurricane is high sea surface temperatures. So as our sea surface temperatures get warmer, and as our atmosphere gets warmer, and it warms the sea, then it's just going to cause more fuel for those hurricanes. And also the intensity are expected to increase. There are some uncertainties, though, as to how global warming will affect its frequency. So we don't know if it'll cause them to happen more often. We just know that, like, say, there'll probably be more intense hurricanes when they do happen. And, we're here in California. We all know forest fires. Hopefully, everybody had power during the last outage. Wildfires are more likely to occur in hot, dry weather in the mid latitudes, and the frequency will increase. So let's hope PG&E figures out the power problem. Okay, so that's everything on the lecture that we have this week. We will be having, well, actually, this week will be our last week of having discussions. From here on out, we will be having some assignments, but the main thing, instead of doing discussions, is that we'll be doing the Green Ninja project. So that project, I will be actually doing a separate recording to kind of help let you guys know, what's due and how that works. I'll be doing that next week, so you guys will be able to see that next week. So I hope you enjoy your week, and I'll see you next time.